So then today, we're going to get into a little bit more complex calculations and ideas involving probabilities. So we're going to add what we call the general addition rule to our list of formulas that we're going to have throughout this unit. We're going to talk about how to use Venn diagrams to help simplify our calculation process. We're going to talk about how to calculate probabilities with two-way tables. And so that's going to be kind of the main focus for today. So the first thing, we need to define this term, mutually exclusive. So when we're looking at mutually exclusive events, we're talking about events that cannot occur simultaneously. And this is going to be a really important term as it applies to our general addition rule today. It's going to actually be a part of some of the later discussions too, as well as like with independence and some of the other topics with probabilities. So this is a really important vocabulary term that you need to know. So mutually exclusive, two events that cannot occur at the same time. Disjoint is another term for mutually exclusive. So those are actually the exact same idea, same definition. So you'll see, like on my answer keys, sometimes I'll use the word mutually exclusive, sometimes I'll use the word disjoint. The book might use the two terms interchangeably, so just understand that those two words mean the same thing. So whether it says disjoint, whether it says mutually exclusive, they're describing the same thing. So as we look at the Venn diagrams here, okay, and we're going to talk about how to create Venn diagrams, how to break down the probabilities and things like that later on in the lesson. But for right now, we're just using them to kind of illustrate this idea of mutually exclusive. So when we do these Venn diagrams, we start with a rectangle that represents our entire sample space. Okay, so when we're looking at the picture there, that rectangle, that's my sample space that has all of the outcomes. So that's the entire collection of outcomes for whatever my random phenomenon is. Okay. And then I have these two circles that are representing events. So yesterday we talked about the idea of sample space being all possible outcomes. Events are subsets. They're a collection of outcomes that satisfy a specific condition. So when we create these Venn diagrams, we have our sample space represented in that rectangle, and then these circles are going to represent the different events that we might be interested in. And so for instance, in a deck of cards, event A might be, So event A might be drawing a diamond from that deck of cards, and event B might be drawing a heart. Now, if we think about those two events as they pertain to our sample space, there's 52 total cards in the deck, but if I define the events drawing a diamond and drawing a heart, as far as this idea of mutually exclusive goes, I have to ask myself, if I draw a single card from the deck, can I draw a card that is a diamond and a heart? So are there any cards in our deck that are both a diamond and a heart? No. So that's what we mean by mutually exclusive. The 13 diamonds and the 13 hearts are completely separate from one another. So those are mutually exclusive. Those are disjoint events. Okay? But in that same deck of cards, if I define the event A to be drawing a red card, and event B is drawing a 4. Now when I think about this scenario here, I got my sample space of 52 cards. I've broken it down into two events, two conditions that I want to apply. The first one is I draw a red card from the deck. The other event is I draw a 4. And so when I ask myself, if I draw a single card from the deck, can I draw a card that is a red 4? Yes. And so if I'm looking at this, I have 26 total red cards. I've got 4 total 4s. How many of those 4s are also red? 2. So there would be 2 outcomes, 2 cards that fall in the overlap, both the 4 of hearts and the 4 of diamonds would fall into that overlap there. Okay? So when we're looking at these mutually exclusive events, we're looking at if I do one single trial of my random phenomenon, can I get a result that works for both events that are defined? So when I wanted to draw a card, I can't draw a card that's a diamond and a heart at the same time. But I can draw a card that's red and a 4. So mutually exclusive versus not mutually exclusive. Some other examples here, because we're going to have lots of different types of problems, not just with playing cards. So take a look at these here real quick and think to yourself, would these events be mutually exclusive or disjoint, or would they not be? And then discuss with the people in your group real quick. So what do you guys think? Mutually exclusive or not? Talk it over with your group. Make sure everyone's on the same page. Okay, so what do we think of that first situation? If I look at the two events, so I'm rolling a single die, I'm looking at the two events, rolling a 3 and rolling a 5. Would those events be mutually exclusive or not? Yes, they would be. So these are mutually exclusive because I cannot roll that dice once and get a 3 and a 5 at the same time. I'm going to get a 3 or I'm going to get a 5. I can't get both. If I look at the second example, randomly selecting a male college student and randomly selecting a math major, would the events selecting a college or male student and selecting a math major be disjoint? No. When I ask myself, could I select a student at random and that student both be a male and a math major? And the answer to that would be yes, I could find that somewhere on campus. So these would not be disjoint. What about the last one? Female blood or blood donor, type A positive, female blood donor. Not going to be disjoint. So not mutually exclusive. Because I could get a female blood donor who is type A positive. Okay? So when you're looking at these scenarios as far as the homework for today, and this is going to show up multiple times throughout the unit, but you always want to be thinking about when multiple events are being described, you want to be thinking about, are these events mutually exclusive? If they are mutually exclusive, we attack them one way. If they're not mutually exclusive, we attack them a different way. So that's kind of what we're dealing with here. Now, this whole idea of mutually exclusive leads us directly into this general addition rule. So this is the first big probability formula that you need to know. Now, this will not need to be memorized. You'll have a formula packet. This will be a formula that's in there. You will need to know when and how to use it. So you'll need to be able to recognize that this is that general addition rule and know the situations that call for it. And so as we're looking at the general addition rule, what we're looking at is the probability that one of two events occur. And so what we're trying to think about is I have these events that are subsets of our sample space. So these are a collection of outcomes that have a certain condition applied to them. And what I'm doing is I'm looking to find the probability that one event or the other happens. And so I've highlighted the word or there. One of the things that makes this particular unit a little more difficult than some of the others, besides the amount of information that we're going to cover in this unit, the questions they ask when they're asking to calculate different probabilities, there's different processes, different formulas we have to use. And a lot of times the questions seem like they're asking the exact same thing every single time. And it's hard to discern or decide when to use this formula, when to use that formula. And so for this particular formula, the general addition rule, you are going to try to key in on the phrase or the word or. It's kind of the main one. What's the probability that this happens or this happens? The other thing that's usually a pretty good giveaway that we're using this general addition rule is I'm performing one single trial. I'm going to draw one single card from the deck. What's the probability I get this or this outcome? I'm rolling the dice one single time. What's the probability that I get this result or this result? I'm picking a single individual from this group. What's the probability that they have this characteristic or this characteristic? So I'm doing a single trial. I'm looking at the probability of getting one thing or another. So as we look at the formula here, the things to key in on, notation, like I said, is going to be really important. So this little union symbol here, this little U, is the symbol we use to denote the English word or. So in set notation, that U stands for union of sets. We interpret it as the word or. So when I write my answers, like this in the homework, this is on your quiz or your test, right? Everything has to have notation. You need to tell me specifically what you're calculating every time. So when they ask you to calculate the probability that this event or the other happens, this is the notation I want to see. Now we talked yesterday too with that notation. I am okay if you were to write this out as the probability of A or B. I wouldn't count off for that. You're doing exactly what I asked you to do. You're telling me specifically what it is you're calculating. But I want you aware of the symbol, because when they give it to you in a problem, or they give it to you in the directions for a set of problems, they're going to use this notation. They're not going to use the word or. So you need to know that that's what that stands for. But if you write the word or, that's not going to be an issue. Now as we look at the formula then, the first part of it is pretty intuitive. If I want this event or the other to happen, it should make sense that I take the probability of the first event plus the probability of the second event. I want all of these outcomes plus all of these outcomes together, because either one would satisfy what I'm looking for. Okay? Now the problem is, and this is where that mutually exclusive discussion we just had comes in. The problem is if my events are not mutually exclusive. So if event A and event B are not disjoint, that means when I do that first part of the equation, so this probability of A means I'm looking at the entire set of outcomes for A. And then when I take that and I put it together with the probability of B, I'm looking at the entire set of outcomes for B. Now, if I just add those together straight up, what problem do I run into? I'm adding some outcomes more than once. So because of that overlap, what's happening is when I add these two probabilities together, if I'm not mutually exclusive, that means I have some outcomes in A that are also in B, right? On that first example that we talked about with mutually exclusive, I said if I have A is red cards and B is the number 4. When I count my red cards, I have 26 red cards. I have 4 4s, but I've used the 2 red 4s twice. I used them in the 26 and I used them in the 4. So I need to take one set of them back out. That's where that minus, that last part of the formula comes in. If I'm not mutually exclusive, there's overlap that I have to account for. And so again, as far as notation is concerned, it's a different color. Okay. This upside down union symbol replaces the word and. So the probability of A and B. This is the intersection of the two events. So when I'm looking at this formula, the A plus B should be pretty intuitive. But if I'm not mutually exclusive, then I have to understand that I've now double counted some of my outcomes. Anything that's in both gets counted twice, so I subtract one set back out. Now, if my events are not, if my events are mutually exclusive, if they are disjoint, so think about my diamonds and my hearts. If I count up all the diamonds, there'd be 13 of them. I count up all the hearts, there's 13 of them. When I put those 13s together, have I double counted anything in that situation? No. So in that case, I don't have to worry about overlap. If they were disjoint to begin with, I can just add the probability straight up, and I'm done. So the other thing you might want to make a note of here, this probability is 0 if the events are disjoint. So this general addition rule will work for any scenario, but if I have disjoint events, I have no overlap, I can simplify the formula by simply taking the probability of A plus the probability of B, and I'm done. There's no overlap to account for, there's nothing to subtract out, so I only have to worry about that when my events are not mutually exclusive. Okay? And so as far as the homework today, you're going to have some questions that involve disjoint events, some that involve non-disjoint events. So knowing how to apply this rule in either instance. A couple of quick examples then. So first question says find the probability of selecting a king or queen or a king from a deck of cards. So if this were a homework problem, first thing you would need to do, tell me what you're calculating in notation. So when I go to set this up, I'm going to calculate the probability of a queen or a king. Now when I write this out, I could use the words queen and king, or I could define them using a specific letter. If I'm going to go queen and king, what would be the letters that would be the most logical to choose? Q and K. So I'm going to define the probability of a Q, queen, or a king. And if you use the word or, that's fine. Just be aware that they're going to use the symbol, so I want you to have exposure to that as much as possible. So probability of a queen or a king. So you're telling me this is exactly what I'm looking for. And now we can actually do the calculation. So we said for that addition rule, probability of a queen, 4 out of 52, plus probability of a king, 4 out of 52. Are these events disjoint? Yes, they are, so I don't have to worry about overlap. And I get my answer directly. So 8 out of 52, which, if you were going to give a final answer, you'd either reduce that. So if you're going to leave it in fraction form, reduce it down, or plug it in your calculator, get the decimal version. Either way is fine. But that's what I would want to see here. So tell me specifically with notation, what am I calculating? Show me how you got your answer, and then give that final answer either in reduced fraction or decimal form. For the second example, similar start, probability of selecting a queen, or this time we change to a club. So if I want to abbreviate, I could use Q and C this time. So probability that we get a queen or a club. And as we start out, we just look at the individual events. Probability of a queen we said was 4 out of 52. Plus the probability of drawing a club would be 13 out of 52. But this time what's happened? They're not disjoint, which means I counted the queen of clubs here and I counted the queen of clubs here. So in that case, I need to subtract out one of those queen of clubs. So there was only the one outcome that overlapped. And so then we would have a 16 out of 52 chance of this, which we would then reduce or plug in the calculator to get the decimal. But this is what I expect to see on these types of calculations. So give me the notation to tell me specifically what you're calculating. Show me the numbers you're plugging in to calculate it, and then whatever the final answer comes out to be. Everyone all right with that? Okay. Next thing here. So another thing we need to be aware of is when we have these non-disjoint events, when I do have these overlaps, there are times where I want to be concerned with specific outcomes in my event, but I want the outcomes that are only for my event. So I don't want the outcomes that are shared with anything else. So if I want to figure out the probability of the outcomes or getting my particular event, but not including the outcomes that also overlap with another event, I take the entire probability of A. So I take all of the outcomes in A, and I subtract out any of those outcomes that also work for B. So again, just getting used to some of that notation there, that upside down union symbol, the intersection means and. So if we're thinking about it in basic terms there in the example, it says probability of drawing a king, but not a heart. So I want to draw a king, I just specifically don't want the king of hearts. So I would have a 4 out of 52. For my king, but I do not want the king of hearts, so I take that one out. So I'd have a 3 in 52 chance of that scenario, which I would reduce or plug in for a decimal for that final probability. Now, this particular formula, this particular calculation, is not usually one that you're going to be asked directly in a problem. This particular process is going to be utilized a lot when we are using other processes to kind of calculate these probabilities, when we're using like Venn diagrams in particular. So what's going to happen here is there's going to be some questions on the homework, on the next quiz, on the next test. I guarantee you're going to see this. I'm going to ask you to be able to create a Venn diagram, so organize the information in a Venn diagram. And so when we look at the scenario that they give us here, it says police report that 78% of drivers stopped on suspicion of drunk driving are given a breath test, 36% are given a blood test, 22% are given both. And so then they want a couple different probabilities, or asking us to calculate a couple of different probabilities. What's the probability that they get a test? What's the probability that they get a blood test or a breath test but not both? What's the probability that they get neither test? So as we're looking at this question here, some of these aren't overly difficult to attack head on. The first question, for instance, says what's the probability that they get a test? So they're saying get a breath or a blood test. So we just talked about that. If I want to calculate that probability, okay, I want the probability that I get a breath test or a blood test. So the probability of getting a breath test was 78%. So 0.78 plus the probability that I got a blood test was 0.36. But are the events disjoint? No, they're not. 22% of people got both. So after I take the 78 plus the 36, I need to subtract out the extra 22% that I double counted. And so if I work that out, we'd have a 92% chance of getting either test. So that particular question, not overly difficult to attack head on. But now if I look at the next one, a blood test or a breath test, but not both. Now this gets a little more complicated because now I got to start thinking about the events where I can't have both people included. And so it gets a little bit more complicated, it gets a little more convoluted as far as how I calculate this out. Now, since they asked me the first question, like in the sequence that we're getting here, the probability that I get a test in general was 92%. Now, if I want to look at blood test or breath test, but not both, what would I have to do? Okay, and the blank stares tells me there's the problem. Okay, this one's not as easy to attack head on. So let's take a step back here. Let's think about the Venn diagram. Okay, this is a tool that we can use. It's going to break the problem down into simpler pieces. So then when they ask the different probability questions, all I have to do is go to my Venn diagram and pick out the pieces I want and put them together. So what's going to happen here is when I create my Venn diagram, so I create my rectangle that represents my entire sample space. I have the two events, event A and event B. Now in this case, we have to define those. So let's say event A is the breath test, and event B is the blood test. Okay. So you would want to make sure you're specific as to which event is which. But what we're going to do then is we're going to just break this down. So as I'm looking at this picture, there's 4 different regions I have to account for. When I look at these regions, this region in the middle, this is the overlap, this is the people who got both tests. This is where we're going to start every time because as far as the question goes, they're going to tell us this specific value. So we're going to start on in the center, in the region that we have that overlap, and then we're going to build from there. Because then I also want to know in this picture, so once I know how much overlap there is, I want to know how many people got a breath test but didn't get both. So that's what this region up here is looking at. The other region down below is what percent of people got blood tests but not both. And then the remaining part, that sample space portion, is anybody who didn't get a test at all. Okay, so those are the 4 regions we're going to break this down into. So we said we start in the middle. They told us in the question, 22% of people get both. So in the middle, we put our 22%. Now, when I go to fill in the other 2 regions associated with my events, this is where I got to be careful. Number 1 mistake kids want to make is they put the 22% in here, and then they go immediately to, well, that means this is my 78 because that's the breath test, and this is 36 because that's the blood test. What's the problem, though? Well, yeah, the probabilities go up to way more than 1, right? Because when I say 78% of people got a breath test, that means the entire circle A total is 78. I'm not filling in the total circle right now. I'm filling in the portion of the circle that had people that got a breath test but not a blood test. So it's not as simple as just taking the percentages from the problem and filling in the regions. The middle, they give me. That one will always be given to you, and they're not mutually exclusive. From there, we have to kind of figure out these other regions. So if all of circle A is supposed to be 78%, we simply took 22% of that out. That 22% goes in the overlap. That leaves me with 56% of people who did get a breath test but nothing else. Likewise, in the other region, if I want the percent of people who got a blood test but nothing else, there were 36% of people that got a blood test. We need to take out the 22 that already got a breath test as well. So there's 14% left over there. Now the only region that I haven't accounted for is the number or the percent of people that didn't get a test at all. So if I think about what we talked about yesterday, if I know all of these regions have these associated percentages, how would I take those and use them to figure out what percent of people didn't have anything? So how can I use these percentages we already filled in to calculate the percent of people that didn't get any test whatsoever? Add them up and subtract from 1. Use the complement rule. These are all the people that got a test. If I subtract those from 1, that should tell me who didn't get a test. So if I subtract those from 1, we get 8% of people that didn't get a test at all. So now, if I want to calculate these questions that they asked me about here, I have everything broken down. All I got to do is pick out the pieces I need and put them together. So what's the probability that they had a test given? Well, that's my top region plus my bottom region plus my overlap. All of these people got tests. There's my 92% like we calculated originally. Now when I look at that second question, we were struggling coming up with how to get there. Now if I look at it with this breakdown, I want a blood test or breath test, but not both. So that means the only two regions I want to account for then are the 56 and the 14. So I put those together. 70% chance they get one or the other, but not both. What's the percent of people that got neither test? Well, we calculated that one directly. I don't even need to do a calculation for that. It's already done. It's just 8%. So these Venn diagrams, like I said, they're an important tool that you can use to break down the problem, simplify some of the percentages a little bit. So then when you start asking questions about different probabilities, all I got to do is go to the specific regions I want, pull those numbers out, and put them together. Okay? So that is something you're going to practice on the homework today. It's something you'll see on the next quiz, so you want to make sure you kind of have an idea of what that looks like. As far as two-way tables, this is actually kind of review. We did a lot of this stuff in Unit 1. Now we're just applying it to specifically probability. So we talked about with these two-way tables, calculating different percentages and things like that. And that's basically what we're doing now. We're just calculating probabilities associated with selecting people at random or whatever the case may be. So in this scenario, they were looking at whether there's a relationship between a particular gene and IQ level. So they took a group of 102 kids. They measured their IQs. They looked to see if they had the particular gene in question, and then they put the information together in the following two-way table. So when we calculate basic probabilities from these two-way tables, we just have to pay attention to what do I want, what are my desired outcomes out of my total, and we got to be careful with what that total looks like depending on how they ask the question. So in this first example here, it says, what's the probability that a child has a high IQ? So in notation, they're asking for a basic probability, just what's the probability that if I select a kid at random, I get a high IQ? So if I'm selecting from all kids, I have the 102 total kids as my denominator. I got to figure out what I want in the numerator there. So if I want a high IQ kid, how many high IQ kids were in the sample? 52. So there's my numerator. And then I would either reduce that or plug it in the calculator and get a decimal version of that. Okay, but all I'm doing when I'm calculating these probabilities, I'm picking whatever number I need from the table, putting it together with whatever sample space is associated with that question, and then calculating the associated probability. So same example, this time they want what's the probability that the child has the gene present. So the probability that they have the gene, still selecting out of all kids, so out of all 102. What's my magic number for this one then? 72. And then I would take that and reduce, or I'd plug in my calculator to get the decimal answer. Okay. And then using kind of what we talked about today. What's the probability that they have the gene or have a high IQ? So now we have that keyword or. If I select a single child at random from this group, what is the probability they have either the gene or the high IQ? So we said when we attack this problem, we start with the individual probabilities. So we already calculated these, the probability that they have the gene. That was 72 out of 102. Plus the probability that they had a high IQ was 52 out of 102. But if I try to add these directly, what problem do I run into? Are these disjoint? They are not. There is overlap. I'm double counting some of the kids in the sample here. So if I take the 72 plus the 52, I then need to account for the overlap. So I have to look at the chart. How many kids had both the gene and a high IQ? 33. So I need to subtract out the extra 33 kids that I double counted. And then whatever that comes out to be, we reduce, plug in our calculator, get the decimal. So however you want to attack that part. Okay. So that takes care of what we need to talk about for today.